Lab 3. Assume that the net force is due to a single force, a gravitational force pulling the star towards a black hole. The black hole is located at the origin. Gravitational force is equal to the gravitational constant g, which is equal to 6.7 times 10 to the negative 11th times meters squared over kilograms squared, multiplied by the mass of the star, which in this case is 1.98 times 10 to the 30th kilograms, and the mass of a black hole, which we don't know, divided by the radius squared, another variable we currently don't know. For this lab, we received a data set which contains the x and y position components for the star. For each set of position pairs, we can compute the velocity of the star at a given moment by taking the change of position over the change of time. From each set of pairs of velocity vectors, we can then calculate the change in velocity. We know from Newton's second law that the net force is equal to the change in momentum over the change in time, which is equal to the mass times the change in velocity over the change in time. Looking at our Python code in VPython, note that star.m is equal to 1.98 e to the positive 30, which is the mass of the star. Also, our delta t is set at 86,400 seconds, which is 1 day. Next, we import the position data and then calculate the velocity, the change in velocity, and the change in momentum, and then the net force as described earlier. Next, we calculate the dp dt, which is equal to Fnet. From Fnet, we want to calculate dp over dt parallel and dp over dt perpendicular. dp over dt parallel is the rate of change of the magnitude of momentum. dp over dt perpendicular is the rate of change of the direction of the momentum. Returning to our code, I have input the equations for dp dt, which is equal to delta p, the change in momentum over the change in time. The net force is equal to dp dt. Next, I calculate dp dt parallel, which is equal to the magnitude of the change of momentum over the change in time multiplied by the unit vector of momentum. The difference between the net force and delta p over delta t is that delta p over delta t is caused by the net force. Additionally, delta p over delta t perpendicular is caused by Fnet perpendicular, and delta p over delta t parallel is caused by the Fnet parallel. To calculate the perpendicular component of dp dt, we learned through vector addition that dp over dt is equal to the perpendicular component of dp over dt plus the parallel component of dp over dt. Therefore, the perpendicular component is equal to dp over dt minus dp over dt parallel, and thus the perpendicular component of the net force is equal to the perpendicular component of dp dt. After setting a small arrow scale, we run our program. Looking at the model, the blue arrow represents the perpendicular component of the net force, the yellow arrow represents the net force, and the black arrow represents the parallel component of the net force. Our output also gives us our net force that we need to calculate the mass of the black hole. The magnitude of the net force, according to our output, is 3.04 times 10 to the 26 newtons. Now we need to calculate the radius of our experiment. First, we assume that the object is moving in a circular motion, so if we take two data points from our spreadsheet, an x and y component, we can calculate the radius of the circle. Since we know that the position of a black hole is at the origin, we can use the other data point to determine the magnitude of the radius. For this example, and using these data points, the magnitude of the radius is 2.98 times 10 to the 12 meters. For our purposes in our force equation, I have also calculated the magnitude of r squared to be equal to 8.92 times 10 to the 24th meters. Now we know all of our variables, so we can calculate the mass of our black hole. By putting in all of our variables, we determine that the mass of the black hole is 2.04 times 10 to the 31st kilograms. Last, if I imagine that the black hole whose mass I found is replaced by a different black hole but placed at the same location, and assuming that the motion of the star remained unchanged, I could not tell the difference between these two black holes. If the mass is different, one of the other variables would have to change too. Therefore, I would not be able to find the value of the mass of the new black hole that is different from the mass of the original one that I have found.